There's some people like that. Okay, I think we'll start the next talk. So it's a pleasure to introduce Lizhi Chen from Lanzhou University. Go take it away. Go ahead, start.
Okay, so should I sit down?
Yes.
I'm very happy to have one opportunity to present my recent work. So today I'm going to talk about the triangulation complexity of hyperbolic manifolds and also its connection to the asymptotic invariant from systolic geometry. So I'll start from some very basic knowledge about hyperbolic manifolds. So a manifold is hyperbolic if it has a Riemannian metric of constant and sectional curvature -1. Equivalently, the manifold M is hyperbolic if it has a hyperbolic structure. So this means the manifold M is homeomorphic to the quotient space, the hyperbolic n space Hn modular discrete subgroup of the isymmetry group of the hyperbolic n space. So for some very basic examples of hyperbolic manifolds in dimension 2, so for here, genus 2 orientable closed surface is hyperbolic. And in dimension 3, so the figure H notch complement is hyperbolic. And then I'm going to talk about the volume of hyperbolic manifolds. First, we know the hyperbolic volume, it is a topological invariant. So in dimension 2, this is given by the corresponding formula. And in dimension at least 3, the most rigidity theorem tells us this fact. And for hyperbolic 3 manifolds, we know the volume satisfies the following two properties. This is given by the theorem of Thurston and Jorgensen. So for the set of volumes of hyperbolic 3 manifolds, it is a well-ordered set, and the order type is omega to omega. And for hyperbolic 3 manifolds, for any given volume, we have only finitely many such hyperbolic 3 manifolds. And for dimension at least 4, we have one finiteness theorem. So this theorem tells us if we give the volume an upbound, then we have only finitely many such hyperbolic manifolds. So the next important invariant is triangulation complexity. The definition for triangulation complexity is now for a manifold M of n dimension, we define the triangulation complexity to be the minimum of the number of n simplices in a triangulation. So in 3 dimensions, the triangulation complexity is exactly the complexity defined by matrix. So if the manifold M is orientable, irreducible, and not homeomorphic to the 3-sphere real projective 3 space and the length space L31. So in the dimension 3, the triangulation complexity should be a natural invariant related to many other aspects of 3 manifolds theory. So recently, I think Professor Lakenby and Professor Purcell in 2019. So they studied the triangulation complexity of 3 manifolds with Fabry over circle. So this is the definition of triangulation complexity. And then I'm going to talk about the simplicial volume. So the definition is we define the simplicial volume to be the infimum of the sum. Here, this sum comes from a cycle C representing the fundamental class in real coefficient homology. And the infimum is over all cycles C representing the fundamental class. And the simplicial volume, so it can be seen as the topological definition of hyperbolic volume because we have this theorem. It is called the Proportionality Theorem. And so the theorem is the simplicial volume is proportional to the hyperbolic. And here the new n, it is a constant only related to the dimension n. So for simplicial volume, because it is defined in real coefficient homology, so I think it's natural to have the triangulation complexity. The triangulation complexity is greater than or equal to the simplicial volume. So we have this relation. The triangulation complexity has a lower bound in terms of the hyperbolic volume. So this is a relation between the two invariants I introduced so far. So one is the hyperbolic volume of the hyperbolic manifolds. Another one is the triangulation complexity. And then I want to introduce another theorem of Jorgensen and Thurston. So this theorem tells us that if we consider a radius the neighborhood of the thick part of a hyperbolic manifold M, then there exists a triangulation. And this triangulation contains at most a constant k times the volume of the hyperbolic manifold. So the tetrahedra cannot be greater than this number. And for here, the constant k is only related to the Margulis constant mu, and so this constant d. And so I introduced this theorem because this theorem will be a bridge between the two sides. So one side is hyperbolic geometry, another side is the asymptotic geometry. So in my title. So now I go to the second part of my talk. I want to introduce one topological invariant from geometrical inequality. Now before I introduce Gromov's systolic inequality, I want to give the definition of essential manifolds. So a closed manifold M is essential if we have a continuous map F from the manifold to a spherical topological space K. It satisfies the induced homology homomorphism, maps the fundamental class to a non-trivial element in the nth homology of the topological space K. And for here, the coefficient, we take integers if the manifold is orientable, and we take the coefficient to be Z2 if the manifold is non-orientable. This is a kind of long definition. So we gave some examples. For all closed hyperbolic manifolds, they are essential manifolds. But also the n-dimensional torus is essential. So in fact, for all spherical closed manifolds, they are essential. So now I can introduce Gromov's systolic inequality. The theorem says if the manifold is closed and essential, then for any Riemannian metric defined of the manifold M, we have this equality. So left side is the shortage length of a non-contractile loop, then to the nth power. The right side is the constant C times the Riemannian volume. This inequality is called is usually called the systolic inequality. So this is one area in differential geometry. Then from the systolic inequality, so I will introduce the definition of systolic volume. So this is the topological invariant from the asymptotic geometry. So the systolic volume is defined to be the optimal constant in Gromov the systolic inequality. So this means in the systolic inequality, the optimal constant C is the systolic volume of the manifold M. So equivalent definition for the systolic volume M can be defined to the infimum of this ratio. So the ratio of the Riemannian volume over the shorted length of non-contractile loop to the nth power. And we take the infimum over all Riemannian matrices. And for this invariant, so I call it systolic volume. We can prove the systolic volume, it is a topological invariant. So in fact, it is a homotopy invariant. So this is proved by Professor Babenko in 1992. And Gromov tells us more. If the manifold is so it's into dimension and it is a closed hyperbolic surface, then the systolic volume, so maybe now we can call it a systolic area, is related to the genus. So in general, for systolic volume, so we have a theorem. So this theorem is still given by Professor Gromov. So for aspherical closed manifold M in dimension n, and we also assume the manifold M has non-zero simplicial volume, then we can find the constant Cn such that the systolic volume is related to the simplicial volume in this way. For this theorem, it is usually called, it is considered to be the central theorem in systolic geometry. So the systolic geometry studies systolic inequality and related geometrical problems. This theorem it tells us, and also some related results implying the systolic volume defined is above. It can be a representation of the topological complexity of the manifold. For here we have an initial question is, can we find more connection between systolic volume and other topological invariants? Especially, previously we have the proportionality principle. So if the manifold M is hyperbolic, then the simplicial volume is proportional to the hyperbolic volume. So in this case, the systolic volume is related to the hyperbolic volume. So now we have a question. So can we study the systolic geometry by using the hyperbolic geometry? So I have tried in this direction. So now I want to introduce a kind of new theorem. So for hyperbolic manifolds of dimension at least 3, we can relate the systolic volume to the triangulation complexity. So in fact, for this result, if we compare to the classical result of Gromov, so it looks like I replace the simplicial volume to the triangulation complexity. So remember previously I had mentioned the triangulation complexity. It has lower bound, the simplicial volume, and the right side, this is the increasing function. So we cannot directly change the simplicial volume to be the triangulation complexity. So this is the main result I want to introduce. Maybe for this, for the triangulation complexity, so it is a natural invariant to represent how complicated the manifold is. So this is maybe one motivation why I want to do this problem. And for the proof of this theorem, so I use previously I introduced the Jorgensen Thurston theorem. So I use this theorem as a tool, combine the hyperbolic volume and Gromov theorem. So I mean this theorem connecting the systolic volume to the simplicial volume. And so this is all I want to present.
Let's thank the speaker. You can unmute if you want. And are there any questions?
Could you give the exact relation between the triangulation complexity and the systolic volume of these manifolds?
Yes. So when the dimension n is greater than or equal to 4, so the systolic volume actually related to the triangulation complexity like this. So on the top should be the triangulation complexity, and the bottom is the logarithm to the nth power. It looks like this because I directly use Gromov theorem between systolic volume and the simplicial volume. And n equal to 3, the result is maybe not as good as it looks like this, because I cannot find the relation between the systolic volume and the injectivity radius. But for n is at least equal to 4, so I can find the relation between systolic volume and the injectivity radius. So this is the relation.
Thank you.
Are there other questions? So perhaps you said this, but are there relations between this triangulation complexity and other sorts of volume concepts that you mentioned earlier?
For triangulation complexity, so if you mention triangulation complexity, I think I have mentioned Professor Lakenby and Professor Purcell's paper. Let me see. So in this paper, so They connect triangulation complexity to the translation length of the three manifolds with multi-class group structure, multi-torus structure. And also in this paper, I think there are lots of results like this. The translation length of the homomorphism file. So, and also I can't remember explicitly the result, but this is a very long paper. It gives many results between triangulation complexity and other things.
Okay. Anyone else have a question? Okay, let's thank Mr. Chen one more time.